Imagine 1,000 people all live in Massachusetts today. Each year, 10% of Californians move east to Massachusetts, and 20% of Massachusetts residents head west to California. After 100 years, how many people live in each state? The answer to extraordinary precision is 2,000 divided by 3 in California, and 1,000 divided by 3 in Massachusetts. And we can find it without simulating a single year. The tool that gets us there is eigenvalues. Here is the migration matrix. A. The top left entry is 0.9, the top right is 0.2, the bottom left is 0.1, and the bottom right is 0.8. Read this matrix by columns. Column 1 tells the story for Californians. Of every person in California, 90% stay in California, and 10% move to Massachusetts. Column 2 tells the story for Massachusetts residents. 20% move to California, and 80% stay in Massachusetts. Notice that each column sums to 1. 0.9 plus 0.1 equals 1. 0.2 plus 0.8 equals 1. That means every person ends up somewhere. No one is created and no one is destroyed. A matrix with this property, non-negative entries and columns that add to 1, is called a Markov matrix or stochastic matrix. Let's take one step. Our starting vector u sub 0 is 0 in California and 1,000 in Massachusetts. Multiply a times u sub 0. For the first row, 0.9 times 0 plus 0.2 times 1,000 equals 200. For the second row, 0.1 times 0 plus 0.8 times 1,000 equals 800. So after 1 year, 200 people are in California and 800 are in Massachusetts. The total is still 1,000, exactly as a Markov matrix promises. After k years, the population vector u sub k equals a to the k times u sub 0. One step was easy, but computing a to the 100th power directly, brutal. That's where eigenvalues earn their keep. Every Markov matrix has a special eigenvalue. Lambda equals 1, always. And here's why it matters. If lambda equals 1 is an eigenvalue, then there's a vector that a leaves unchanged. That vector is the steady state. To find the second eigenvalue, we use the trace. The trace of a is the sum of the diagonal entries. 0.9 plus 0.8 equals 1.7. But the trace also equals the sum of the eigenvalues. So lambda 1 plus lambda 2 equals 1.7. Since lambda 1 is 1, lambda 2 must be 0.7, two eigenvalues free of charge, 1 and 0.7. Now let's find the eigenvectors. For lambda equals 1, we solve the equation a minus I times x equals 0. Subtracting the identity matrix from A gives us the matrix with rows negative 0.1, 0.2 on top, and a 0.1, negative 0.2 on the bottom. The first row tells us that negative 0.1 times x1 plus 0.2 times x2 equals 0. Solving this gives x1 equals 2 times x2. If we pick x2 equals 1, then x1 equals 2, so the first eigenvector is the column 2, 1. Now for lambda equals 0.7, we form a minus 0.7 times I, which gives us rows 0.2, 0.2 on top, and 0.1, 0.1 on the bottom. The first row says 0.2 times x1 plus 0.2 times x2 equals 0, which simplifies to x1 plus x2 equals 0. So x1 equals negative x2. Choosing x2 equals 1 gives the eigenvector negative 1, 1. So we have our two eigenvectors, 2. 1 corresponds to the steady state with eigenvalue 1, and the negative 1. 1 corresponds to the decaying part with eigenvalue 0.7. Pause for a moment on that negative 1 in the second eigenvector. Does a negative population make sense? Of course not. But here's the key idea. The eigenvector isn't a population by itself. It's a direction in solution space. Our actual population vector, u sub k, is a combination of both eigenvectors, and that combination always stays non-negative. The negative entries cancel out properly when we add the pieces together. Now let's write down the general solution. U sub k equals c1 times 1 to the k times the vector 2, 1 plus c2 times 0.7 to the k times the vector negative 1, 1. We have two unknowns left to find, c1 and the c2. Now we find c1 and c2 using the initial condition. At k equals 0, u sub 0 is the vector 0, 1000. Plugging in, we get c1 times the vector 2, 1 plus c2 times the vector negative 1, 1 equals 0, 1000. That gives us two equations, one from each component. The first component says 2c1 minus c2 equals 0. The second component says c1 plus c2 equals 1000. From the first equation, c2 equals 2c1. Substitute that into the second equation. c1 plus 2, c1 equals 1000, so 3c1 equals 1000, giving c1 equals 1000 over 3. Then c2 equals 2000 over 3, and we're done. The complete solution is u sub k equals 1000 over 3 times the vector 2, 1 plus 2000 over 3 times 0.7, to the k times the vector negative 1, 1. Let's do a quick sanity check at k equals 0. Start with the first term, 1000 thirds times the vector 2, 1. That gives 2000 thirds, 1000 thirds. Now the second term, 2000 thirds times 0.7 to the 0, which is just 1, times the vector negative 1, 1. That gives negative 2000 thirds, 2000 thirds. Now add them. The first entry is 2000 thirds minus 2000 thirds, which equals 0. The second entry is 1000 thirds plus 2000 thirds, which equals 1000. So the total is 0, 1000. That matches u sub 0 exactly. Notice the two pieces are doing different jobs. The first piece is constant. It's the steady state direction. The second piece shrinks every year by a factor of 0.7, so it fades away as k grows. Now watch what happens as k goes to infinity. The factor 0.7 raised to, the k shrinks towards 0, so the entire decaying term vanishes. Only the steady state survives, so u infinity equals 1000 thirds times the vector 2, 1, which gives 2000 thirds in the first component and 1000 thirds in the second. That's 2000 thirds of a person in California, and 1000 thirds in Massachusetts. Adding them up, 2000 thirds plus 1000 thirds equals 3000 thirds, which is exactly 1000. Conservation holds, no one was created or lost. Now notice the ratio, 2 to 1. California ends up with twice as many people as Massachusetts. That 2 to 1 ratio is baked right into the eigenvector 2, 1. It does not depend on where everyone started. If we had put all 1000 people in California instead, or split them 500 each, we would still converge to the very same 2 to 1 ratio. Initial conditions only change the constants c1 and c2. They change how fast we get there, not where we end up. Step back for a moment and see what just happened. We replaced computing a to the 100th power, a truly horrible calculation, with one scalar power, 0.7 raised to the 100, which is essentially 0. Diagonalization turned matrix powers into scalar powers. The eigenvalue with magnitude 1 gave the steady state. The eigenvalue with magnitude less than 1 decayed away. That is the entire trick, and it generalizes beautifully. Google PageRank ranks web pages by finding the lambda equals one eigenvector of a giant stochastic matrix built from links between pages. Weather forecasting models transitions between states like sunny, cloudy, and rainy. And the long-run climate is the steady-state eigenvector. Population genetics tracks gene frequencies the very same way. In every case, build a Markov matrix where the columns sum to 1, find the lambda equals one eigenvector, and that vector tells you the equilibrium. One trick, endless applications. So the next time someone asks where 1000 people will live after 100 years of migration, you do not need a simulation. you just need the eigenvector 2, 1, and the answer falls right out. 2,000 thirds in California, 1,000 thirds in Massachusetts.